Okay, welcome to topic 2.2. We're going to start by talking about what's called the axiomatic method, and that is starting with a set of assumptions or presuppositions, another way of saying that, or accepted truths or postulates is what we call them. So it's starting with these things that can't necessarily be proved, but we just accept them. Okay. For example, I don't want to get an example. All right, the axiomatic method. Here's an example. The system we are developing in this class is called Euclidean geometry. And Euclidean geometry is a system built on certain assumptions. One of the big assumptions, basically, to sum up these assumptions, is that we're on a flat surface. We're on a flat surface, but not all surfaces are flat. So the geometry we're learning in this class, we're assuming flatness. It's called Euclidean geometry. It is a system of mathematics that works on flat planes and is built using deductive reasoning, meaning we're assuming things and we're using those assumptions to make other claims. Deductive reasoning, which means that we make conclusions based off of previously accepted statements. Or I think that's how you spell. There's two C's in accepted, right? Yes. Or assumptions accepted to be true. A postulate, or another word for this is axiom, is a statement that is accepted without proof. No proof needed. We also call these, axioms. There it is. So for example, here's our postulates. And what these postulates do is they put us on a flat surface. Through any 2 points, there's exactly one line. If I make 2 points, I get one line. You might say, well, yeah, what else could there be? If I was on a curved surface, which I can't really show you, then I could technically go through the paper and hit both of those points, and that would be different. So we are on a flat surface, so we're accepting this as truth. A line contains at least 2 points. These are kind of the same. If we go back to the last lesson, this is saying 2 points imply a line. And this one's saying a line implies 2 points. So these are just converses of each other. If you can remember what that's about from the last lesson. This is P implies Q. This is Q implies P. Converses. Postulate 2.3. If 2 lines intersect, then the intersection is exactly 1 point. You get a line, and you get another line, and you only get one intersection point. They do not curve back and intersect again. They don't do that. They keep going forever and will never ever intersect again. 2.4. Through any 3 non-collinear points, this is getting back to chapter 1 a little bit here, there exists exactly one plane. If you got 3 points, then you got a spider web. A plane contains at least 3 non-collinear points. So once again, 3 non-collinear points implies a plane. A plane implies 3 non-collinear points. These are converses. P implies Q, Q implies P. And postulate 2.6. If 2 points lie in a plane, then the line containing them lies in the plane. So if you've got yourself a plane, and you've got yourself these points that are in the plane, then this line also must be in the plane. This line cannot curve out of the plane. It can't do that. It's stuck. If these points are in the plane, then this line is also stuck in the plane. Now remember, the plane goes forever. It's like we almost need to draw planes like this. The plane goes forever. We just don't put lines. Like on the line, we actually put little arrows like that. And so it's easier to think. If two planes intersect, then the intersection is a line. If two planes intersect, think of it like this. I've got this plane. I've got this plane. This is a line. They're intersecting right here. Think of that as like a line. So when two planes come together, they make a line. Next. A logical argument in which each statement is supported by a statement, that's called a proof. The P word, proof. Proof is this is true because that was true. And this is true because that was true. And this is true because that was true. It's truth based on truth. A statement that has been proven is called a theorem. What's the difference between a theorem and a postulate? A theorem requires a proof. The Pythagorean theorem has been proven. That's why I call it the Pythagorean theorem. It's actually been proven 351 times. Different ways. So there's lots. The reasons that we can use in deductive reasoning include the following. They include theorems. We can use theorems to make new theorems. We can use postulates to make new theorems. We can use accepted definitions to make new theorems. And we can use properties that we've accepted. Like, we'll get into those in a little bit later. So now what I've done is I've taken all of your vocabulary words that you've gotten up to this point. These are all the definitions. So we have definitions for all of these. And definitions are all biconditionals. So we can write all of our definitions in the if and only if. So here's what I mean by that. I'm going to just fill these in real quick. An acute angle, if and only if the measure is between 0 and 90. Obtuse is between 90 and 180. A right angle is exactly 90, and a straight angle is exactly 180. Alright, so working through those. Pause and reflect if you have to. Two angles or segments are congruent if and only if they have the same measure. Segments will have the same length. Angles will have the same degree. Adjacent. The angles have a common vertex. And side. Angle bisector has to go through, has to divide the angle into two congruent angles. When in doubt, put congruent. Complementary. I can make that C, turn it into a 9, which helps to remember 90. Supplementary. I can take that S and turn it into an 8, which helps you remember 180. So 9, 8, 180. Collinear. 3 points if and only if they lie on the same line. Midpoint. A midpoint has to make two congruent segments. And a segment bisector has to go through a midpoint. Opposite rays have to have the same endpoint and form a straight angle. Straight. It says straight. It's kind of small. Perpendicular lines form right angles. Linear pair, if and only if they have a common vertex and a non-common sides are opposite rays. Just put OPP for opposite. And then vertical angles formed by two intersecting lines that are not adjacent. Okay, so pause, go back. If this was class, I would have you pair up and try to figure out as many of these as possible, and then I'd go over them with you. So that's how we're doing that. Alright, here is our first proof. This proof is based off of these postulates. Here we go. Ready? Postulate number 1. Money is the root of all evil. So we can write money is, is always equal in a math equation. So money is the root, square root, of evil, E for evil. So if we accept that postulate, then we can use it to make a theorem. Postulate 2. Time is money. You ever heard of that? Time is money. So we can write that mathematically. Time is money. Time is money. Postulate 3. Girls require time and money. Ooh, that's interesting. Do you accept that postulate? If you accept that postulate, then we can make a theorem. So mathematically, girls are time and money. Time times money. That's what that is. So we're going to try to prove that girls are evil. We got girls and we got evil. Can we connect it all together using some math, some properties that we accept? Alright, so the first thing is this is called a two-column proof. Two-column proof. The first column is your statements. Your second column is the reasons why you can make that statement. So why can I make the statement that girls equal time and money? I can make this statement because that's an accepted postulate. I can make this statement, time equals money, because that's an accepted postulate. Now I can use an accepted property. It's called the substitution property, where instead of writing girls equals time times money, what can I substitute in for time? What can I replace time with? I can take time and replace it with money. As I said, time is equal to money. So instead of writing time times money, I can write money times money, because time is money. So instead of time times money, I got money times money. And then we would all agree from algebra, substitution property, that m times m is equal to m squared. So we can take this and substitute for this. M times m equals m squared. Then we can bring in this truth, so I can say this because of postulate 1. Remember postulate 1? Money equals the root of all evil. And then this is an accepted truth of algebra. If you square both sides, right, this cancels off. So now we're left with money squared equals evil. And money squared is here, and money squared is here. So here's what I got. I got girls equal money squared, and money squared equals evil. Girls equal money squared equals evil. Let me write that out. Girls equal money squared, and money squared equals evil. Girls are evil. So there you have it. So now this is a theorem. We proved it. We used postulates to prove that girls are evil. Therefore, that's what that means. Theorem 1, girls are evil. How do you feel about that? That sounds pretty fun. Now, this is only true if you accept these postulates. If you do not accept these postulates, then this falls apart. You could run this same proof with boys require time and money. So, there you go. Alright. Got time? State the reason for the statement. Alright, so in this scenario, we've got two planes, plane L and plane K, and they intersect at plane PS. So oh, that's the end of school. Planes L and plane K intersect at line PS. Well, that reminds me of this postulate, which says if two planes intersect, then the intersection is a line. So backing up that is postulate 2.7. Next, points U, M, and O are coplanar. Points U, M, and O are coplanar. Well, that reminds me of through any three non-collinear points, there exists one plane. So postulate 2.4. You do not have to know the numbers. This is the only time we'll ever reference these numbers. You have to know, you have to understand the gist of the postulates. You got to be able to fill in blanks. I might just do blanks like this on a quiz. You got to be able to fill them in. Angle QOP is a right angle. How do I know that QOP is a right angle? You probably see this square. And so the reason that I can state that is the kind of like the definition of the right angle symbol. We know that this means right angle, so that's how that works. Line MQ is in plane K. Do you agree that Q is in K? Do you believe that O is in K? So if 2 points lie in a plane, then the line containing them also lies in the plane. That's postulate 2.6. And then lastly, line PS and line MQ intersect at point O. If two lines intersect, then the intersection is 1 point. That was postulate 2.3. Alright. Next. I said properties are, we can use them in proofs. So let's review some of the properties that we have. And these come straight from algebra class. So the addition property. If you add something to one side, you have to add it to the other side. The goal of algebra is to balance the universe. If A is equal to B, then A plus C will balance with B plus C. If I add C to one side, I have to add C to the other side. And now we are still in balance. Subtraction property. If I subtract C from one side of the equation, I have to subtract C from the other side. If we start with this, then this is okay. If we start with this, the multiplication property, and if I multiply by C on one side, I multiply by C on the other side. So if this is balanced, then this is still balanced. If this is balanced, A over C is equal to B over C. As long as I divide, if I divide on one side, I have to divide on the other side to keep things balanced. There's one exception here. C cannot equal 0. You cannot divide by 0. The reflexive property. This also works for congruent. So, the reflexive property, it just says this. Anything is always equal to itself. A is equal to A. That's it. Anything is equal to itself. Symmetric property. It means you can flip. If A equals B, then B equals A. If A is equal to B, then B is equal to A. If 2 is equal to X, then X is equal to 2. And you use that all the time in algebra. Certain words are also symmetric. If Bob is a brother to Fred, then Fred is a brother to Bob. So, brother is symmetric. It's a symmetric word. Transitive. If A is equal to B and B is equal to C, so this is like a, think of like a train. Transitive, kind of. It's like putting the train together. A is connected to B, B is connected to C, so therefore A is equal to C. Substitution property. If A is equal to B, then A may be replaced with B. You can replace it. You can substitute in an A for a B. And lastly, the distributive property. This is one of your favorites from algebra. If A times the quantity B plus C, then that is equivalent to A times B plus A times C. So those are just some algebra properties. Next video.